Think for a moment about where everything around you, the stars, the planets, even the atoms in your body came from. The answer lies in a single, explosive moment nearly 14 billion years ago, the Big Bang. But what if I told you that the story doesn't end there? That hidden within the fabric of the cosmos are clues so astonishing, they rewrite our understanding of how the universe began. From ripples in space-time to the mind-bending concept of cosmic inflation, scientists have uncovered discoveries so profound, they challenge everything we thought we knew about reality itself. Today we're diving into 25 of the most incredible findings about the Big Bang and the explosive expansion that shaped our universe, revelations that will leave you in awe of the cosmic drama playing out all around us. Picture this: a universe smaller than a single atom, hotter than the core of a star, and in an instant gone, not vanished but stretched, expanded, and transformed in a fraction of a second faster than the blink of an eye. This is cosmic inflation, the wild, almost unbelievable theory that explains why the universe looks the way it does today, and here's the kicker: we have actual evidence for it. Tiny fluctuations in the afterglow of the Big Bang, imprinted like fingerprints on the sky, tell us that the universe didn't just grow, it exploded into being with a force so unimaginable, it defies logic. But how and why? The answers lie in some of the most groundbreaking observations ever made, from the cosmic microwave background to the large-scale structure of the universe itself. You might be wondering, why does any of this matter? Because these aren't just abstract ideas, they're the foundation of our existence. Every atom, every galaxy, every law of physics traces back to that primordial fireball and the mysterious forces that shaped it. And the craziest part, we're still uncovering new pieces of the puzzle, from quantum ripples stretched across the cosmos to the possibility of parallel universes. The Big Bang and cosmic inflation aren't just history, they're a living, breathing mystery, one that scientists are racing to solve. So buckle up, because we're about to take you on a journey through space and time, to the very edges of what we know and beyond. By the end, you'll never look at the night sky the same way again. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were tinkering with a strange horn-shaped antenna in New Jersey, trying to eliminate persistent background noise interfering with their satellite communications. No matter what they did, adjusting equipment, cleaning out pigeon droppings, the static remained. What they didn't realize at first was that this annoying hiss wasn't a flaw in their technology. It was the echo of creation itself. They had stumbled upon the cosmic microwave background, the oldest light in the universe, lingering from the Big Bang like the faint warmth of a campfire long after the flames have died. This accidental discovery earned them a Nobel Prize and handed scientists a time machine, a way to peer back to when the cosmos was just 380,000 years old. The CMB isn't just any radiation, it's a near-perfect snapshot of the infant universe, cooled over billions of years to just 2.725 degrees above absolute zero. But here's what's mind-blowing: its uniformity. No matter where astronomers look, the temperature varies by less than 100,000th of a degree. That smoothness was a puzzle. How could regions of space billions of light years apart, which had no time to exchange heat or information, be so perfectly matched? The answer would come from cosmic inflation, the theory that the universe underwent a faster-than-light expansion in its first split second, stretching quantum ripples into the vast, whisper-thin variations we see today. These tiny fluctuations became the seeds for everything: galaxies, stars, even the voids between them. Without those imperfections, gravity would have had nothing to cling to, and the cosmos might have remained a featureless sea of particles forever. What makes the CMB so revolutionary is how it transformed cosmology from speculation into precision science. By mapping its subtle wrinkles with satellites like COBE, WMAP, and Planck, researchers have decoded the universe's composition, age, and even its fate. Those faint microwaves carry fingerprints of dark matter, dark energy, and the very geometry of space-time. Think of it as a cosmic barcode, one that, when scanned, reveals secrets hidden since the dawn of time. And the wildest part, we're still deciphering its message. Every new observation peels back another layer, challenging what we thought we knew about the universe's birth. So the next time you see static on an old TV screen, remember, you're glimpsing the afterglow of the Big Bang, a remnant so ancient, it outshines every star in the sky. But the cosmic microwave background wasn't just a relic, it was a riddle. For decades, the Big Bang theory had two glaring holes that kept scientists up at night. First, the horizon problem. Why does the universe look so similar in every direction, even in regions too far apart to have ever interacted? Second, the flatness problem. Why is space so perfectly balanced between expanding forever and collapsing back on itself, like a pencil standing on its tip for billions of years? Enter Alan Guth, a physicist who, in 1980, proposed a solution so radical it rewrote cosmology: cosmic inflation. His idea was simple yet staggering. In the first trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe didn't just expand, it underwent a violent, exponential growth spurt, doubling in size at least 60 times faster than the speed of light. This wasn't just wild speculation. Inflation made testable predictions. It explained the horizon problem by suggesting that the entire observable universe was once a tiny, interconnected speck, stretched to cosmic proportions in an instant. The flatness problem. Inflation would have smoothed out any curvature like pulling tight a wrinkled sheet, leaving space eerily flat. But Guth's boldest prediction was about those faint temperature variations in the SIMB. Inflation wouldn't just stretch space, it would stretch quantum fluctuations, too, imprinting them as microscopic density differences that later grew into galaxies. When satellites like COBE finally mapped these variations in the 90s, they matched inflation's predictions with uncanny precision. It was as if the universe had left a signature, and Guth had cracked the code. What's astonishing is how much this explains. Without inflation, the universe's large-scale structure makes no sense. Those quantum ripples, magnified to cosmic scales, became the scaffolding for everything: the great walls of galaxies, the voids between them, even the distribution of dark matter. And inflation didn't just solve old puzzles, it created new ones. If space expanded faster than light, could there be regions of the universe still inflating beyond our horizon? Are we just one bubble in an endless multiverse? These questions push the boundaries of physics, but they all trace back to Guth's breakthrough. His theory turned cosmology from a collection of mysteries into a science with predictive power, showing us that even the wildest ideas can be tested, if we're brave enough to look. Here's where things get truly mind-bending. Those tiny quantum fluctuations, random blips of energy at the smallest scales imaginable, ended up shaping the entire universe. Think of it like this: imagine blowing up a balloon with microscopic dots drawn on its surface. As the balloon inflates, those tiny marks stretch into vast patterns. That's exactly what happened during cosmic inflation, but instead of dots, it was quantum jitters, fluctuations so small, they're governed by the bizarre rules of particle physics. In the first moments of the universe, these ripples were stretched exponentially, frozen into the fabric of space-time as inflation expanded the cosmos faster than light itself. And here's the kicker: we can still see these ripples today. The cosmic microwave background isn't perfectly smooth, it's dotted with faint temperature variations, some slightly warmer, others cooler. These aren't random, they're the stretched-out fingerprints of those primordial quantum fluctuations, imprinted on the sky like a cosmic fossil. When satellites like Planck mapped these variations with stunning precision, they revealed something extraordinary. The patterns matched exactly what inflation predicts. Those minuscule quantum ripples became the gravitational seeds for everything. Regions of slightly denser space attracted matter, while lighter areas became voids. Over billions of years, gravity amplified these differences, pulling matter into galaxies, clusters, and the vast cosmic web we see today. What's astonishing is how delicate this balance was. If those quantum fluctuations had been even slightly weaker, matter might never have clumped together, leaving the universe a dark, empty sea. Too strong, and gravity would have collapsed everything into black holes before stars could form. Instead, we got Goldilocks perfection, fluctuations just right to create a universe filled with structure, yet stable enough for life to emerge. It's as if the universe played a cosmic game of dice, and we're here because the numbers landed exactly as they did. But the story doesn't end there. These fluctuations also carry clues about inflation's energy. The way they're distributed, their size, their spacing acts like a recording of inflation's engine, telling us how violently space expanded. Some theories suggest inflation was driven by a mysterious field called the inflaton, a kind of cosmic fuel that powered the expansion before fading away. Others propose even wilder ideas, like connections to string theory or higher dimensions. What's clear is that these quantum ripples are more than just ancient relics. They're a Rosetta Stone, helping us decode the universe's earliest moments. And with every new observation, we're getting closer to understanding how nothingness gave birth to everything. In 2014, the scientific world erupted with excitement when researchers working with the BICEP 2 telescope at the South Pole announced they'd found the smoking gun of cosmic inflation, primordial gravitational waves. These weren't just any ripples in space-time, they were theorized to be echoes from the universe's first trillionth of a second, stretched to cosmic scales by inflation's violent expansion. The signal they detected appeared as a distinct twisting pattern in the cosmic microwave background, known as B modes, which seemed to match exactly what inflation predicted. For a brief moment it felt like cosmology's holy grail had been found, with headlines proclaiming a breakthrough worthy of a Nobel Prize, but science has a way of humbling even the most confident claims. As other teams scrutinized the data, a problem emerged. The twisting patterns BICEP 2 observed could also be caused by something far more mundane, interstellar dust within our own Milky Way. By 2015, joint analysis with the Planck satellite confirmed the heartbreaking truth: the signal was contaminated. Those swirling imprints weren't cosmic inflation's fingerprints after all, but the glow of ancient dust grains, polarized by magnetic fields over billions of years. The announcement that once seemed to confirm inflation's wildest predictions had to be walked back, a sobering reminder of how tricky it is to tease cosmic truths from noisy data. Yet this wasn't just a scientific misstep, it was a masterclass in how real discovery works. The BICEP 2 episode forced researchers to refine their methods, leading to more sophisticated dust mapping techniques and collaborations between rival teams. It also revealed something profound: the line between noise and discovery is razor thin. Those same B modes could still hide inflation signal, buried beneath the dust. Future telescopes, like the Simons Observatory and Lightbird, are now designed to separate cosmic whispers from galactic interference with unprecedented precision. What looked like a failure became a stepping stone, proving that even dead ends push science forward. The takeaway isn't that inflation is wrong, it's that the universe guards its secrets fiercely. Gravitational waves from the Big Bang remain the ultimate prize, a direct window into physics at energies 1 trillion times beyond what particle colliders can reach. If detected, they'd reveal not just how inflation happened, but what fueled it, whether it was an inflaton field, string theory vibrations, or something even stranger. The BICEP 2 story is a reminder: in cosmology, answers rarely come easily, but every setback sharpens the search, bringing us closer to the day when we finally hear the universe's first faint tremors. While the BICEP 2 saga showed how hard it is to tease cosmic truths from noisy data, another mission was quietly rewriting the textbook on the Big Bang with precision so staggering, it felt like upgrading from a blurry Polaroid to a high-resolution telescope. Enter the European Space Agency's Planck satellite, a cosmic detective that spent 4 years staring into the afterglow of creation, mapping the cosmic microwave background with such razor-sharp accuracy, it turned faint whispers into a roaring chorus of revelations. Launched in 2009, Planck was designed to capture the CMB's temperature variations down to millionths of a degree, like detecting a snowflake's weight difference on opposite sides of a mountain. What it found didn't just confirm earlier estimates, it refined them with surgical precision. The universe's age, 13.8 billion years, give or take a mere 39 million, a blink in cosmic terms. Its composition, a recipe so bizarre it reads like science fiction, 5% ordinary matter, 27% dark matter, and a staggering 68% dark energy, a mysterious force accelerating the universe's expansion. But Planck's real triumph was how it transformed abstract numbers into a cosmic origin story. By analyzing the CMB's faintest fluctuations, it revealed that space is geometrically flat to within a razor-thin margin, just a 0.4% deviation from perfect flatness. Think of it like rolling a marble across an infinite table. Planck showed the table isn't just large, it's flawlessly level, a smoking gun for inflation's smoothing effect. Even more startling was the mission's measurement of the universe's expansion rate, known as the Hubble constant. Planck's value clashed with later measurements from nearby galaxies, sparking a modern cosmic mystery called the Hubble tension, a discrepancy that hints at gaps in our understanding of physics itself. What makes Planck's legacy so enduring isn't just the data, it's how the mission forced scientists to confront the universe's strangeness head-on, those painstakingly mapped temperature variations. They're not perfectly random. Some patterns appear slightly stronger at larger scales, a possible fingerprint of inflation's energy or even exotic physics like cosmic strings. And the way dark matter and dark energy's ratios were refined didn't just fill in gaps, it deepened them. If dark energy is truly constant, why does its apparent strength seem to shift subtly across time? The beauty of Planck is that its data remains a goldmine, still being sifted for clues. Every reanalysis peels back another layer, like finding hidden tracks on a vinyl record no one knew existed. Future missions will build on its work, but Planck's map of the infinite universe stands as a landmark, a reminder that precision isn't just about numbers. It's about hearing the universe's first cries with crystal clarity and realizing how much we still have left to decode. One of the most astonishing revelations from the cosmic microwave background is something that sounds deceptively simple: the universe is flat. Not flat like a sheet of paper, but flat in the language of geometry, meaning parallel lines stay parallel forever, and the angles of a triangle always add up to exactly 180 degrees. This isn't just a mathematical quirk, it's a direct window into the universe's origins and its ultimate fate. When scientists first mapped the CMB's temperature fluctuations with missions like COBE and WMAP, they were secretly hunting for a cosmic curve, some telltale bend in space-time that would reveal whether the universe was closed like a balloon, open like a saddle, or perfectly balanced between the two. What they found was far more surprising. The universe isn't just approximately flat, it's flat to within a margin of error so razor-thin, it's like measuring the smoothness of a marble the size of Earth and finding no bump taller than a single atom. This near-perfect flatness, represented by the symbol omega, equaling almost exactly one, wasn't just a lucky coincidence, it was a smoking gun for cosmic inflation. Picture it like this: imagine blowing up a wrinkled balloon to the size of a planet. Those tiny creases would stretch out so completely, the surface would appear flawless to the naked eye. Inflation did the same thing to the universe, smoothing out any primordial curvature in a fraction of a second, leaving space so flat, it defies classical intuition. But the implications go far beyond geometry. A flat universe is a universe poised on a knife's edge between expansion and collapse. If omega were even slightly less than 1, gravity would eventually reverse the Big Bang, pulling everything back into a fiery, big crunch. If it were greater, space would stretch so thin, galaxies would rip apart into isolated islands of darkness. Instead, we're left with a cosmos expanding just fast enough to avoid collapse, but not so fast that structure never formed, a Goldilocks scenario that hints at something deeper. This precision flatness also ties directly to the universe's composition. For omega to equal 1, there had to be exactly enough matter and energy to balance the equation, a mix that later observations revealed as ordinary matter, and dark energy. Without that delicate equilibrium, the geometry would warp, and the CMB's patterns would look radically different. It's as if the universe's blueprint included a hidden instruction: stay flat, no matter what. What's even wilder is what flatness says about the cosmos's future. A perfectly flat universe suggests expansion will continue forever, growing colder and emptier until the last stars flicker out. But there's a twist: dark energy's accelerating push could mean space doesn't just expand, but does so exponentially, eventually tearing apart even atoms in a big rip. Or perhaps some unknown physics will rewrite the rules entirely. The magic of this discovery is how it connects the infinitesimal to the infinite. Those faint temperature spots in the CMB imprinted by quantum fluctuations smaller than a proton determined whether the universe would curve back on itself or stretch into oblivion. And somehow, against all odds, it chose the path that allowed galaxies, planets, and us to exist. Flatness isn't just a feature of the universe, it's the foundation of its story, written in geometry and whispered across billions of years. If the universe's flatness hints at a delicate cosmic balance, the story takes an even stranger turn when we fast forward to 1988. That's when two rival teams of astronomers made a discovery so shocking, it upended everything we thought we knew about the cosmos. By observing distant supernova exploding stars so bright, they outshine entire galaxies, they expected to measure how much the universe's expansion was slowing down due to gravity's pull. Instead, they found the opposite. The universe wasn't just expanding, it was accelerating, as if some invisible force were pushing space apart faster and faster with each passing moment. This wasn't just a small tweak to the rules, it was a cosmic revolution. The only explanation: a mysterious repulsive force called dark energy, making up nearly 70% of the universe's total energy. Picture it like this: imagine throwing a ball into the air, only to watch it shoot upward faster and faster, defying gravity entirely. That's what dark energy does to the fabric of space itself. But here's the real kicker: this force isn't new. It's been there since the Big Bang, lurking in the background, waiting for gravity's grip to weaken enough for its influence to dominate. What makes dark energy so baffling is how little we understand it. Einstein once proposed a similar idea, his infamous cosmological constant, but abandoned it as his greatest blunder. Turns out he might have been right for the wrong reasons. Some theories suggest dark energy is the energy of empty space itself, a property woven into the vacuum. Others propose it's a dynamic field, like inflations in flatten, but operating on cosmic timescales, or perhaps it's a sign our understanding of gravity is incomplete, a crack in Einstein's theory of relativity. The implications are staggering. If dark energy keeps accelerating expansion, the distant future of the universe looks bleak. Galaxies beyond our local group will eventually vanish over the cosmic horizon, their light stretched beyond detectability. Billions of years from now, astronomers in our Milky Way will peer into an empty sky, with no evidence other galaxies ever existed. It's a lonely fate, one that raises eerie questions. Are we living in the only era where cosmic history is still visible? A fleeting window where the afterglow of the Big Bang and the glow of distant galaxies share the same sky? Yet dark energy also ties back to inflation in a poetic twist. Both involve rapid expansion driven by mysterious energy fields. Some theorists speculate they might be different faces of the same phenomenon, one shaping the universe's birth, the other its death. It's as if the cosmos bookends its story with two explosive acts, a violent beginning and a slow-motion finale. The discovery of accelerating expansion didn't just win its teams the Nobel Prize, it rewrote the cosmic playbook. Suddenly, the fate of the universe wasn't just about how much matter it contained, but about an unknown force controlling its expansion, and the wildest part. We're still in the dark about what dark energy truly is. Future telescopes like the Vera Rubin Observatory and ESA's Euclid mission are hunting for clues in the large-scale structure of galaxies and the bending of light by dark matter. Every new observation peels back another layer of this mystery, reminding us that the universe's greatest secrets are still hiding in plain sight. Imagine the universe in its infancy, a seething, unimaginably hot soup of particles, just minutes old. In this cosmic cauldron, the first atoms were forged, setting the stage for everything that would follow, and here's the incredible part: we can still glimpse the echoes of that primordial chemistry today. The key lies in helium, the universe's second lightest element. According to the Big Bang Theory, within the first 3 to 20 minutes after the initial explosion, conditions were just right for nuclear fusion to occur on a cosmic scale. Protons and neutrons collided, forming helium nuclei, but only up to a point. Once the universe cooled enough, this process slammed shut like a vault, freezing the elemental recipe in place. The predictions were precise. About 25% of the universe's ordinary matter should be helium by mass, with the rest almost entirely hydrogen. And when astronomers pointed their telescopes at the oldest stars and the most distant gas clouds, that's exactly what they found. These ancient cosmic relics, untouched by later stellar processes, held a helium abundance of 24.85%, a match so uncanny, it felt like reading a fingerprint left by the Big Bang itself. What makes this discovery so groundbreaking is how it locks in the universe's earliest moments. The exact amount of helium depends on factors like the density of protons and neutrons, and how quickly the cosmos expanded and cooled. If the Big Bang hadn't unfolded exactly as theorized, if those first minutes had been hotter, colder, faster, or slower, that ratio would be off. Instead, it's a perfect cosmic receipt, confirming not just that nucleosynthesis happened, but how it happened. But the story gets even richer. The remaining 75% hydrogen wasn't just idle filler. It became the fuel for the first stars, the raw material for galaxies, and eventually, the atoms in our bodies. That tiny fraction of helium, it's the ash of the universe's first and most violent furnace, a relic so pervasive, it's in every breath you take. And here's the twist: this helium abundance also acts as a cosmic speedometer. By measuring it, scientists can indirectly clock how fast the universe expanded in those critical first minutes. Too fast, and there wouldn't have been enough time for neutrons and protons to combine into helium. Too slow, and the soup would have cooked too much, turning more hydrogen into heavier elements. The observed 25% is the Goldilocks result, another silent witness to the fine-tuning of the cosmos. The beauty of this discovery isn't just in the numbers, it's in the way it connects the dots between theory and observation. Big Bang nucleosynthesis didn't just predict helium, it also foresaw trace amounts of lithium and deuterium, a heavy form of hydrogen. And again, the universe delivered. The lithium abundance matches within a few percent, while deuterium levels act like a cosmic thermometer, revealing the universe's temperature during those frenzied first minutes. Yet this isn't just a victory lap for the Big Bang Theory. The primordial helium abundance also raises tantalizing questions. Why, for example, does the observed lithium content fall slightly short of predictions? Could there be new physics at play in the early universe? Or is it a clue about how matter and antimatter annihilated each other? These tiny discrepancies aren't flaws, they're breadcrumbs, leading us toward deeper mysteries. So the next time you hear about helium, whether it's filling party balloons or cooling MRI machines, remember, you're handling a substance older than the stars. A relic from a time when the entire universe was a single, seething nuclear reactor, forging the elements that would one day build planets, life, and us. It's a humbling thought. The same process that lit up the cosmos also left a calling card, a helium signature that says, "This is how it all began." One of the most puzzling gaps in our understanding of the Big Bang isn't about what's there, it's about what's missing. According to everything we know about particle physics, the early universe should have created equal amounts of matter and antimatter, particles and their mirror image counterparts that annihilate on contact in bursts of pure energy. So why does everything we see, stars, planets, even our own bodies, consist solely of matter? This isn't just a small oversight, it's a cosmic crisis. If matter and antimatter had been perfectly balanced, they would have wiped each other out entirely, leaving a lifeless void. The fact that we exist at all means something tipped the scales. The search for this asymmetry, known as baryogenesis, has led scientists down a rabbit hole of exotic theories. Take leptogenesis, for instance. This idea suggests that ultra-heavy neutrinos, particles so elusive they barely interact with ordinary matter, decayed unevenly in the early universe, creating a slight excess of matter over antimatter. How slight? We're talking about one extra matter particle for every 10 billion matter-antimatter pairs that annihilated. That razor-thin imbalance was enough to seed everything we see today, a cosmic lottery win against impossible odds. What's fascinating is how particle accelerators like the Large Hadron Collider are hunting for clues. By slamming protons together at near light speeds, they recreate conditions not seen since the universe was a trillionth of a second old, searching for rare particles that might violate the expected symmetry between matter and antimatter. So far, the most promising hints come from studying kaons and B-mesons, unstable particles that occasionally decay in ways that favor matter over antimatter. These deviations are tiny, far too small to explain the universe's matter dominance, but they prove the asymmetry is real, yet the mystery runs deeper. Some theories suggest the answer lies not in particles but in the fabric of space-time itself. Cosmic inflation, the universe's explosive growth spurt, might have stretched tiny quantum fluctuations into macroscopic imbalances, separating matter and antimatter into distant pockets. If true, there could be entire antimatter galaxies lurking beyond our observable horizon, forever out of reach. Others propose even wilder ideas, like parallel universes where antimatter dominates, or that the missing antimatter collapsed into hidden dimensions. The stakes couldn't be higher. Solving this puzzle wouldn't just fill a textbook gap, it would rewrite our understanding of how existence itself emerged from nothingness. Every experiment, from neutrino observatories buried deep underground to telescopes scanning the cosmic microwave background, is chasing the same question: why is there something rather than nothing? And until we find the answer, the universe's greatest disappearing act remains its most tantalizing enigma. Zoom out far enough and the universe reveals an astonishing secret, a vast, intricate web of galaxies stretching across billions of light years, connected like neurons in a cosmic brain. This isn't random chaos, it's a carefully woven tapestry of matter, one that traces its origins back to those quantum ripples stretched by inflation. And the map to decode this grand design, the Sloan Digital Sky Survey, one of the most ambitious astronomy projects ever undertaken, which spent years painstakingly cataloging the positions of millions of galaxies. What it uncovered was nothing short of revolutionary, a colossal skeleton of galaxy clusters, filaments, and voids, arranged in patterns that match inflation's predictions with eerie precision. The scale of this structure is hard to grasp. Imagine a network where each thread is a chain of galaxies millions of light-years long, converging at dense nodes where thousands of galaxies swarm like bees around a hive. Between them lie deserts, immense voids so empty, a single galaxy might drift alone for hundreds of millions of years. This cosmic web isn't just beautiful, it's a frozen echo of the universe's infancy. Those faint temperature variations in the cosmic microwave background, they're the blueprint for this architecture, the seeds around which gravity sculpted everything we see today. Here's where it gets even wilder. The Sloan survey didn't just map galaxies, it measured their light so precisely, scientists could reconstruct how matter clumped together over cosmic time. And the data lined up perfectly with inflation's playbook. Those quantum fluctuations, initially smaller than an atom, grew into the gravitational wells that pulled in gas, birthing the first stars and galaxies. The voids, they're the inverse, regions where slightly less density meant gravity lost the tug of war, leaving behind emptiness. It's as if the universe were a canvas, and inflation's brushstrokes dictated where the paint would pool and where it would fade. But the real triumph was how these observations silenced skeptics. Alternative theories like cosmic strings or defects in space-time predicted very different large-scale patterns, ones that surveys like Sloan definitively ruled out. Instead, the data revealed a universe where galaxies cluster in ways that only make sense if inflation's exponential stretching happened. The statistical fingerprints of those primordial ripples are baked into the distances between galaxy clusters, the angles where filaments intersect, even the way voids stack like bubbles in foam. What's equally breathtaking is how this web keeps evolving. Recent surveys like DAISY and Euclid have added 3D motion to the map, showing how galaxies flow along filaments like water rushing through rivers, pulled by the gravity of dark matter. These flows aren't random, they're the universe's way of continuing the construction project inflation started, with gravity as the foreman, and just like the CMB, the cosmic web isn't just a relic, it's a time machine. By studying its patterns, we can peer back to an era before galaxies existed, when the universe was a dark sea of gas, waiting for gravity to flip the switch. The beauty of this discovery is what it tells us about our place in the cosmos. Our Milky Way isn't floating in isolation, it's part of the Laniakea supercluster, a gargantuan filament in the web, slowly drifting toward a gravitational hotspot called the Great Attractor. Every galaxy, every star, every atom is part of this grand structure, one that began as a whisper in the first trillionth of a second after the Big Bang. And with every new survey, we're adding more details to the map, uncovering a story written not just in starlight, but in the invisible scaffolding of dark matter and the ghostly imprint of inflation itself. This is the power of the cosmic web. It doesn't just show us where things are, it reveals how they got there, tracing a line from quantum jitters to the splendor of the universe we call home. Hidden within the cosmic microwave background's nearly flawless map lies something that shouldn't be there, a bizarre, large-scale pattern so statistically improbable, cosmologists call it the axis of evil. This isn't just a quirky name, it's a genuine cosmic glitch that defies one of cosmology's most sacred principles, the idea that the universe is isotropic, meaning it should look the same in every direction. Yet when scientists analyzed the CMB's temperature fluctuations across the sky, they found an eerie alignment, a strange correlation between hot spots and cold spots that traces an axis through space, almost as if the universe had a preferred direction. The discovery first emerged in 2006, when researchers studying data from NASA WMAP satellite noticed something unsettling. The quadrupole and octupole moments, the large-scale patterns in the CMB weren't randomly oriented as inflation predicts. Instead, their axes aligned with the ecliptic plane of our solar system, an alignment so precise, the odds of it happening by chance were less than 1 in 1,000. It was like rolling a pair of cosmic dice 100 times and getting snake eyes every single time. Skeptics argued it might be an artifact of foreground contamination or measurement bias, but follow-up observations by the Planck satellite only deepened the mystery. The axis persisted, stubbornly refusing to vanish under scrutiny. What makes this anomaly so unsettling is how it chips away at the foundations of modern cosmology. The Big Bang model relies on the assumption of statistical isotropy that the universe has no preferred direction, no cosmic up or down. Without this symmetry, many of our calculations collapse like a house of cards. If the axis of evil is real, it could mean our universe isn't just lopsided, it might be fundamentally different on scales larger than we can observe, hinting at anything from exotic physics to a pre-Big Bang structure imprinted on space-time. Some theorists have proposed radical explanations. One idea suggests the anomaly is a fingerprint of cosmic topology, evidence that our universe is finite and multiply connected, like a hall of mirrors on a cosmic scale. In such a universe, light could wrap around and create repeating patterns, mimicking an axis. Others speculate it's a remnant of a collision with another universe during inflation, a bruise left by a long-ago encounter in the multiverse. And then there's the most spine-chilling possibility, that we're seeing the shadow of something beyond our cosmological horizon, a structure so vast, its gravitational influence warps the CMB across observable space. Of course, not everyone is convinced. Critics point out that human brains are wired to find patterns, even in randomness, a phenomenon called pareidolia, like seeing faces in clouds. Could the axis of evil just be a statistical fluke, amplified by our tendency to overinterpret noise? Maybe, but with each new CMB map, the signal lingers, whispering that there's more to the story. Future missions like CMB-S4 aim to settle the debate with hypersensitive measurements, peeling back the layers of this cosmic onion to see if the axis is a mirage or a revolution waiting to happen. The deeper we look, the clearer it becomes. The universe delights in appending our expectations, whether the axis of evil is a flaw in our models, a window into new physics, or just a cosmic coincidence. It's a reminder that the Big Bang's afterglow still holds secrets, ones that might rewrite the rules of reality itself. While the cosmic microwave background gives us a snapshot of the universe at 380,000 years old, there's a crucial chapter missing from that picture: the dawn of the first stars. For hundreds of millions of years after the Big Bang, the cosmos was a dark, murky sea of neutral hydrogen gas, too cold and diffuse to glow. Then, somewhere around 300 million years in, something extraordinary happened. The first stars flickered to life, and their searing ultraviolet radiation blasted through the cosmic fog like a superheated knife, tearing electrons from hydrogen atoms in an event so transformative, scientists call it the epoch of reionization. These weren't just any stars, born from pristine clouds of hydrogen and helium. They were monsters hundreds of times more massive than our Sun, burning ferociously hot and dying young in spectacular supernova. Their UV light acted like a cosmic bleach, stripping electrons from atoms and reionizing the gas that had been neutral since the CMB's release. The universe went from opaque to transparent again, but this time not because of cooling, because of light. Here's the mind-blowing part. We can see this epoch's fingerprints in the CMB's polarization data. When WMAP and later Planck studied how the CMB light waves align, they found subtle swirls called E modes and B modes, patterns etched by free electrons scattering photons during reionization. It's like finding ripples in a pond long after the stone was thrown. The disturbance remains, telling a story of that first violent burst of starlight. The timing of reionization is its own puzzle. By measuring how much the CMB's light was twisted by these free electrons, scientists pegged the epoch's midpoint at roughly 450 million years after the Big Bang. But recent observations of ancient galaxies like GNZ 11, spotted by the James Webb Space Telescope, suggest some regions may have ignited stars and begun reionizing earlier than we thought. Could patches of the universe have emerged from the darkness while others still slumbered? The data hints at a messy, uneven process, more like a campfire spreading than a single light switch flipping. What's at stake isn't just a timeline. Reionization shaped the universe's structure. Those early stars didn't just light up the cosmos, their death seeded it with heavier elements, forging the carbon, oxygen, and iron that would later build planets and life. Their radiation also heated the remaining gas, stifling the growth of petite galaxies and setting the stage for the massive ones we see today, yet mysteries linger. If the first stars were as colossal as theories suggest, why haven't we spotted more of them? Could exotic objects like black holes or dark matter particles have contributed to reionization? Every new observation from Webb's deep field images to next generation SIMBI experiments brings us closer to answering how the universe woke up from its dark ages, turning on the lights for everything that followed. While light and matter have told us so much about the Big Bang, there's an entire ghostly population of particles that have slipped through our detectors unnoticed until now. Meet the cosmic neutrino background, the universe's most elusive fossil. These relic neutrinos were born just 1 second after the Big Bang, when the cosmos was still a seething plasma 10 billion times hotter than the Sun's core. As space expanded and cooled, these particles so lightweight they barely interact with anything streamed outward, untouched by the collisions and chaos that shaped protons and electrons. Today they permeate every cubic inch of the universe, including your body, passing through you at nearly the speed of light by the trillions every second. Detecting them is like trying to catch smoke with a butterfly net. Unlike the cosmic microwave background, which paints the sky with microwaves, relic neutrinos carry no electric charge and almost no mass, making them nearly invisible to conventional instruments. Their energy is staggeringly low, about 10,000 times weaker than the CMB photons, equivalent to the vibration of a single atom, barely moving at room temperature. Yet these whisper-thin particles hold secrets about the universe's infancy that light alone can't reveal. That's where projects like Ptolemy come in. This audacious experiment, buried deep underground to shield from cosmic noise, aims to catch relic neutrinos using ultra-cold graphene sheets and radioactive tritium. The idea: when a neutrino collides with a tritium nucleus, an event rarer than winning the lottery 10 times in a row, it might emit a detectable electron. It's a moonshot, but if successful, Ptolemy could open a window into the first second of cosmic history, revealing how neutrinos shaped the early universe's expansion, and even how their tiny masses influence the growth of galaxies. What makes relic neutrinos so revolutionary isn't just their age, it's what they can teach us about physics' greatest puzzles. Their minuscule masses, for instance, could hint at undiscovered particles or forces active in the universe's first moments. And because neutrinos rarely interact, they've traveled billions of years undisturbed, preserving information about conditions we can't see any other way. It's like finding a diary from the Big Bang's first breath, written in a language we're just learning to read. But here's the twist: these ghostly particles might also be sculpting the cosmos today. Simulations suggest relic neutrinos could subtly tug on dark matter, shaping how galaxies cluster over billions of years. Even more bizarre, some theories propose they're entangled with dark energy, their wispy gravitational pull opposing the universe's accelerating expansion. If true, the key to cosmology's biggest mysteries might be hiding in these ancient, nearly massless particles, if only we can catch them. The hunt for the cosmic neutrino background is more than a technical feat, it's a testament to human curiosity. Every time a detector is upgraded or a new method proposed, we're inching closer to touching the untouchable, to hearing whispers from a time before stars or atoms existed. And when we finally succeed, it won't just fill a gap in our knowledge, it'll rewrite the story of how everything began. What if our universe isn't the only one? What if it's just one bubble in an endless cosmic foam, part of a multiverse where countless other universes bloom and fade beyond our reach? This isn't science fiction, it's a stunning prediction of cosmic inflation, a theory so powerful, it doesn't just explain our universe's birth, it suggests the Big Bang might have happened over and over again. The idea is called eternal inflation, and it's as mind-bending as it sounds. Picture inflation as a pot of water boiling violently. Most bubbles pop instantly, but a few grow so fast they outpace the simmering chaos around them. In cosmic terms, those surviving bubbles are universes like ours, each with its own laws of physics, its own constants, even its own dimensions. The key lies in quantum fluctuations, in tiny, random jumps in energy that, during inflation, could have created pockets where the expansion slowed just enough for matter and galaxies to form. Everywhere else, inflation keeps raging eternally, birthing new universes in an unending cascade. The implications are staggering. If eternal inflation is real, it means our universe is fine-tuning the perfect balance of gravity, electromagnetism, and other forces might not be a miracle, but a coincidence. In an infinite multiverse, every possible combination of physical laws would exist somewhere. We just happen to live in the rare bubble where conditions allowed stars, planets, and life to emerge. It's like winning a cosmic lottery where the prize is existence itself, but how could we ever prove something so outlandish? Some theorists suggest looking for bruises on the sky, ancient collisions between our universe and neighboring bubbles that might have left scars in the CMB's patterns. Others propose that gravity could leak between universes, subtly warping space in ways future telescopes might detect. And then there's the wildest idea of all, that black holes might be portals to other universes, their singularities birthing new cosmic realms beyond the event horizon. Philosophically, eternal inflation forces us to confront humbling questions. Are we just one thread in an infinite tapestry? Does the multiverse render our existence trivial or more precious? For some, it's a vision of cosmic loneliness, a universe adrift in an unfathomable sea of others. For others, it's a promise of boundless creativity, a cosmos where every possibility, no matter how strange, plays out somewhere. One thing's certain, if eternal inflation is true, the Big Bang wasn't a one-time event. It's still happening endlessly in realms we'll never see, and that means the story of our universe isn't just about how we began, it's about how beginnings themselves might be written into the fabric of reality. The Hubble constant, the rate at which our universe expands, sounds like one of those straightforward numbers in cosmology. Plug it into equations, and you should get the same answer no matter how you measure it. But here's the twist, the universe seems to be playing a cosmic shell game with us. When scientists calculate this number using the cosmic microwave background, they land on roughly 67 kilometers per second per megaparsec. Yet when they measure it using supernova or pulsating stars in the nearby universe, the value jumps to around 73. That 6-kilometer gap might sound tiny, but in cosmology, it's a chasm, one so significant, it sparked a crisis called the Hubble tension. So why does this discrepancy matter? Because it's not just a rounding error. The CMB method peers back to the universe's infancy, relying on the afterglow's detailed patterns to extrapolate today's expansion rate. The supernova method, meanwhile, measures bright exploding stars in our cosmic backyard, tracking how fast galaxies are racing away. Both approaches are meticulous, both have been refined for decades, and both insist their numbers are rock solid. Yet they stubbornly refuse to agree. This isn't just a case of scientists needing better calculators, it's a glaring sign that something fundamental is missing from our understanding of the cosmos. The leading suspicion, an unknown ingredient in the universe's recipe, maybe dark energy isn't constant but evolves over time, subtly tweaking the expansion rate. Or perhaps dark matter interacts with itself in ways we haven't accounted for, throwing off the cosmic balance. Some theorists even float the idea of an extra, lightweight particle, like a dark radiation, that slipped through the early universe unnoticed, altering how structures formed. The wildest proposals suggest gravity itself might behave differently on cosmic scales, breaking Einstein's rules in ways we've never detected before. What's fascinating is how this tension has turned into a battleground for competing visions of physics. One camp argues the gap could vanish with better data, blaming hidden errors in measurements like dust obscuring supernova or quirks in how CMB light polarizes. Others think we're on the brink of a revolution where reconciling these numbers might require rewriting textbooks. The stakes couldn't be higher. If the Hubble tension is real, it wouldn't just tweak our models, it could crack them wide open, revealing physics beyond the standard model or even hints of a multiverse. The race to solve this puzzle is heating up. Next-generation telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope are poised to deliver the most precise measurements yet, while lab experiments hunt for exotic particles that could fill the gap. Until then, the Hubble tension remains one of cosmology's most tantalizing mysteries, a cosmic tug-of-war between what we think we know and what the universe is trying to tell us. And the answer, whatever it is, could change everything. Imagine the early universe as a vast, seething ocean not of water, but of plasma so hot, light couldn't escape. Within this primordial soup, sound waves rippled outward like cosmic echoes, compressing and rarefying matter in their wake. These weren't ordinary sound waves, though. Traveling at nearly half the speed of light, they left behind a permanent signature, one that scientists today use as a cosmic measuring tape, known as Baryon acoustic oscillations, or BAO. These ancient pressure waves froze in place when the universe cooled enough for atoms to form, imprinting their rhythm onto the distribution of galaxies. Here's how it works. In the first few 100,000 years after the Big Bang, the universe was a roiling mix of protons, electrons, and photons, all tightly coupled like dancers in a frenzied tango. Gravity would pull matter inward, while the intense radiation pressure of photons would push it back out, creating oscillations regions of slightly denser and sparser matter. These vibrations traveled outward until the moment of recombination, when atoms formed and the universe became transparent. Suddenly, the music stopped. The waves froze mid-ripple, leaving behind spherical shells of matter at a very specific distance from their origin, about 500 million light-years apart. Fast forward billions of years, and those frozen waves are still visible. When astronomers map the positions of millions of galaxies, they find a curious pattern. Galaxies are slightly more likely to be separated by this exact distance, as if the universe had stamped them with an invisible ruler. It's like tossing pebbles into a pond and later finding all the leaves floating at the same distance from where each ripple began. This predictable spacing makes BAOs one of cosmology's most powerful tools, acting as a standard ruler to measure how the universe has expanded over time. The brilliance of BAOs lies in their simplicity. Unlike supernova or CMB measurements, which rely on complex physics or assumptions about brightness, Baryon oscillations offer a geometric test. By comparing the known size of these ancient sound waves, determined from the CMB, to their apparent size in galaxy surveys, scientists can calculate how much the universe has stretched and thus how fast dark energy is pushing it apart. Projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have used BAOs to chart the cosmos in 3 dimensions, revealing the subtle tug-of-war between gravity's pull and dark energy's push. But BAOs aren't just about expansion, they also encode secrets about the universe's composition. The way galaxies cluster around these acoustic peaks reveals how much dark matter is present, since its invisible gravity sculpts the large-scale structure. The spacing of the peaks even hints at the number of neutrino species in the early universe, offering a window into particle physics that no lab on Earth can match. What's truly astonishing is how these sound waves bridge scales, from the quantum fluctuations of inflation to the vast cosmic web we see today. They're a direct link between the universe's fiery birth and its present-day architecture, a fossilized echo that whispers across billions of years. And with every new galaxy survey, we're tuning our instruments to hear that whisper more clearly, uncovering not just how the universe grew, but why it grew the way it did. The next time you look up at the night sky, remember, the galaxies above aren't scattered randomly, they're dancing to the rhythm of a song that began in the first microseconds of time. Among the many cosmic mysteries, one of the most puzzling is the discovery of magnetic fields threading through galaxy clusters, stretching millions of light-years far larger than anything today's astrophysics can easily explain. These colossal magnetic forces shouldn't exist, at least not according to conventional wisdom. They're too vast, too uniform, and too strong to have formed solely from stars or black holes. The leading theory: they might be relics from the Big Bang itself, fossilized remnants of a primordial magnetism woven into the fabric of space-time during the universe's earliest moments. The idea isn't as far-fetched as it sounds. During cosmic inflation, the same quantum fluctuations that seeded galaxies could have also generated microscopic magnetic fields. As inflation stretched space exponentially, those fields would have been magnified to cosmic scales, imprinting space itself with a faint but pervasive magnetic signature. Later, when galaxies and clusters formed, these primordial threads could have acted like invisible scaffolding, guiding the growth of cosmic structures while amplifying into the colossal fields we detect today. But here's the catch: we've never directly observed these primordial fields. Instead, we see their fingerprints in the way charged particles spiral through galaxy clusters, emitting telltale radio waves and X-rays. Experiments like the Planck satellite have hunted for subtle twists in the cosmic microwave background that might betray their presence, while radio telescopes scour distant gas clouds for hints of magnetization predating the first stars. So far, the evidence is tantalizing but indirect, like finding rust on an ancient tool but never seeing the hand that held it. The implications, though, are staggering. If primordial magnetism is real, it would mean the universe was born with invisible forces already at work, shaping cosmic evolution from the very first instant. Some theories even suggest these fields could explain dark matter's elusive nature or provide clues about the inflatoned field that powered inflation. Others propose they're remnants of exotic phase transitions in the early universe, moments when space itself underwent violent reorganizations, leaving behind magnetic scars. Of course, skeptics argue these fields could still be the product of later astrophysical processes, supernova explosions, black hole jets, or even cosmic rays. But the scale remains a problem. How could random stellar events create magnetic coherence across millions of light years? Unless, of course, they're piggybacking on something much older, something written into the universe's blueprint before the first stars flickered to life. The hunt for these ancient fields is far from over. Upcoming observatories like the Square Kilometre Array promise to map magnetism across the cosmos with unprecedented precision, potentially spotting fields so faint and old they predate galaxies themselves. If they succeed, we might finally glimpse a hidden layer of cosmic history, one where magnetism wasn't just a byproduct of the universe's growth but a foundational force, as intrinsic to the Big Bang as space and time. Until then, these ghostly magnetic threads remain one of cosmology's great unsolved riddles, whispering that even after 14 billion years, the universe still guards secrets from its very first moments. Stephen Hawking's most shocking revelation wasn't about the birth of the universe, it was about its death. In the 1970s, he made a startling prediction: black holes aren't truly black. They glow, they leak, they slowly evaporate into nothingness through a phenomenon now called Hawking radiation. But this elegant solution came with a terrifying catch. When a black hole finally vanishes, all the information about what fell into it seemingly disappears too. Gone, erased from reality, this wasn't just a problem for black holes, it was a crisis for physics itself, because quantum mechanics insists information can never be lost. The universe, it seemed, had a paradox at its core, one that traces straight back to the Big Bang's fiery beginnings. At first glance, black holes and the Big Bang couldn't seem more different. One crushes matter into oblivion, the other birthed it from nothing. But dig deeper, and they share an eerie similarity. Both are singularities, points where gravity becomes infinite and the laws of physics break down. The Big Bang singularity gave birth to time and space, black holes twist them into knots, and just as Hawking radiation threatens to erase information in black holes, the explosive birth of the universe raises the same haunting question: if everything emerged from a singularity, where did the information about its initial state go? This puzzle cuts to the heart of modern physics. Quantum mechanics governs the microscopic world with strict rules. Every particle's position, spin, and history is encoded in its wave function, a mathematical fingerprint that can't simply vanish. Yet general relativity, Einstein's theory of gravity, treats space-time like a smooth stage where information can fall behind a black hole's curtain, never to return. The conflict between these two frameworks isn't just academic, it's a rift in our understanding of reality. Either our theories are missing something fundamental, or the universe plays by rules we haven't yet imagined. Enter the holographic principle, one of the boldest attempts to resolve the paradox. It suggests that all the information swallowed by a black hole isn't lost, it's smeared across its event horizon like a cosmic etching, a two-dimensional projection of three-dimensional reality. Apply this idea to the Big Bang, and suddenly the singularity isn't a dead end, it's a transformation. The information about the universe's birth might not be destroyed, just remapped onto the boundaries of space-time itself. It's as if the cosmos keeps its receipts, storing the fine print of creation in places we're only beginning to look, yet the stakes are higher than theoretical neatness. If information truly vanishes in singularities, it undermines our ability to predict the past or future. The Big Bang becomes a cosmic reset button, wiping the slate clean of whatever came before. But if the holographic principle or rival ideas like string theories add S/CFT correspondence holds the answer, it could mean the universe has a hidden layer of order, a deep structure that preserves causality even in the face of infinite gravity. That's why labs worldwide are hunting for hints of quantum gravity, the missing link that could reconcile relativity and quantum mechanics. From experiments measuring space-time's granularity to detectors listening for echoes of black hole mergers, each discovery peels back another layer of the paradox. And with every step forward, we're not just solving a puzzle about black holes, we're decoding the universe's own origin story, learning how something as fragile as information can survive the most violent events in existence. The answers, when they come, won't just tell us about the end of stars, they'll reveal how the beginning of everything left its mark on reality itself. The universe's most violent transition wasn't the Big Bang, it was the moment inflation stopped. Picture a cosmic roller coaster hurtling forward at unimaginable speed, only to slam into a wall, transforming its kinetic energy into a fireball of heat and light. That's reheating, the catastrophic end of cosmic inflation, when the universe's exponential expansion shattered into a seething plasma, igniting the hot Big Bang we know today. For all its brilliance, inflation couldn't last forever. The inflated field, the mysterious energy driving this hyper-expansion, was inherently unstable. Like a stretched rubber band, it carried potential energy that had to snap back. When it finally decayed, it didn't just fizzle out, it unleashed a tsunami of particles and radiation. In less than a trillionth of a second, the frigid, stretched-out quantum vacuum of inflation erupted into a churning furnace, heating the cosmos to temperatures exceeding a billion degrees. Space, once frozen in exponential growth, suddenly became a roiling sea of quarks, gluons, and leptons, the raw ingredients of everything that would follow. What's astonishing is how little we know about this pivotal moment. Reheating wasn't a gentle simmer, it was a turbulence of particle creation, where inflated energy fragmented into violent, chaotic bursts. Some theories compare it to water freezing into ice crystals. As the inflated field crystallized into stable configurations, it released shockwaves that ripped through the newborn universe, colliding and thermalizing into equilibrium. Others suggest it resembled a supercharged version of radioactive decay, with inflated particles self-destructing into showers of matter and radiation. The stakes of this transition can't be overstated. Without reheating, the universe would have remained a cold, empty void. The thermal energy it unleashed set the stage for nucleosynthesis, quark-gluon plasma, and ultimately, the formation of atoms. But reheating did more than just heat the cosmos, it sculpted it. Tiny inhomogeneities in how the inflaton decayed could explain why some regions of space ended up denser than others, seeding the galaxies and voids we see today. It's even possible that reheating generated gravitational waves, faint enough to evade detection, but strong enough to leave faint imprints in future CMB observations. Yet mysteries abound. Did reheating happen uniformly, or in fiery pockets? Could some corners of the universe still be inflating while others reheated, as eternal inflation suggests? And what if dark matter was forged not in stars or the Big Bang, but in the crucible of reheating's particle collisions? The answers might lie in relics we've yet to discover, exotic particles hiding in plain sight, or subtle distortions in the CMB's polarization. For now, reheating remains one of cosmology's most pivotal black boxes, the violent bridge between nothingness and everything. And the more we learn, the clearer it becomes. The universe's beginning wasn't a single event, but a chain reaction of chaos, each step rewriting the rules of reality itself. While cosmic inflation has become the leading explanation for the universe's early moments, it's far from the only idea on the table. Some theorists argue that the cosmos didn't just expand once, it's been collapsing and rebounding in an endless cycle, like a cosmic accordion. Others propose that before our Big Bang, there was another universe contracting toward a big crunch, only to bounce back in a fiery rebirth. These alternative visions, cyclic models, and bouncing cosmologies offer dramatically different origin stories, but when stacked against the cosmic microwave background's meticulous map, their plots start to unravel. Take the cyclic model, championed by physicists like Paul Steinhardt and Neil Turok. In this scenario, our universe is one page in an infinite flipbook, where parallel, brane worlds collide periodically in higher dimensional space, triggering new Big Bangs without singularity or inflation. It's an elegant idea, but the CMB throws a wrench in the works. Cyclic models predict a very different pattern of temperature fluctuations, ones that lack the precise Gaussian randomness inflation's quantum ripples would produce. When Planck's team analyzed the CMB statistics, they found inflationary fingerprints everywhere. The fluctuations weren't just random, their distribution matched inflation's predictions to within 1%, a blow to cyclic theories that rely on smoother, more ordered beginnings. Bouncing cosmologies face similar hurdles. These models suggest our universe emerged from a prior collapsing phase, avoiding a true singularity by bouncing back thanks to quantum gravity effects. But here's the problem: a bounce would leave scars. The violent contraction would amplify pre-existing gravitational waves to deafening levels, creating a cacophony of B-mode polarization in the CMB far stronger than what's observed. When Bicep 2's dust-contaminated signal was cross-checked with Planck, the upper limits on these primordial gravitational waves were so low, they ruled out most simple bounce scenarios. Yet the most damning evidence lies in the universe's large-scale structure. Inflation's exponential stretching explains why distant regions of space look so similar. They were once in causal contact before inflation blew them apart. Cyclic and bouncing models struggle to replicate this uniformity without fine-tuning. They also can't easily explain the CMB's near-perfect flatness, or the specific spectrum of galaxy clustering revealed by surveys like Sloan. It's as if the universe left a trail of breadcrumbs, and inflation is the only theory that follows them all the way home. That's not to say these alternatives are worthless. They've pushed cosmologists to test inflation's limits, asking whether its predictions are truly unique or if tweaked versions of rival ideas could survive. Some hybrid models, like ekpyrotic scenarios, borrow elements from both inflation and bounce theories, proposing slower, non-exponential expansion before the Big Bang. Others suggest that while inflation dominates our observable universe, other regions might follow different rules in a greater multiverse. What's striking is how the CMB has become the ultimate arbiter. Its temperature variations, polarization patterns, and statistical properties act like a cosmic Rosetta Stone, translating abstract theories into measurable predictions. The fact that inflation's forecasts keep matching the data from the Gaussian fluctuations to the acoustic peaks doesn't just support one idea, it demonstrates the power of modern cosmology to test visions of reality we once thought untouchable. The next time you hear about the Big Bang, remember, its best evidence isn't just in the stars, but in the cold, quiet glow between them. The first second of the universe wasn't just a moment, it was a laboratory for physics beyond our wildest imagination. At temperatures exceeding a billion degrees, the forces we know today as separate electromagnetism, the strong and weak nuclear forces, were fused into a single, unified superforce. This was the realm of grand unification theories, or GUT, where the laws of physics operated at energies so extreme, they're a trillion times beyond what our most powerful particle colliders can recreate. If we could rewind to inflation's peak, we'd witness a reality where particles didn't just behave differently, they were different. Take the hypothetical inflaton, the enigmatic field thought to have powered cosmic inflation. Unlike any particle in the Standard Model, the inflaton wasn't just a passenger in the early universe, it was the engine. Picture it as a cosmic syrup, thick with potential energy, stretching space until its own decay triggered the Big Bang's fireball. But here's the twist, the inflaton might not have been alone. GUTs predict a menagerie of exotic particles, X and Y bosons, magnetic monopoles, even primordial black holes that could have been forged in inflation's furnace. These aren't just theoretical curiosities, they're the missing links between quantum mechanics and gravity, relics of a time when the universe's rules were written in a language we're still struggling to decipher. The stakes of this puzzle are sky high. If grand unification is real, it would mean that the four fundamental forces we observe today are just fragments of something far grander, frozen remnants of a broken symmetry. Imagine watching ice crystals form and realizing they're all shards of the same shattered pane. That's what GUTs suggest happened as the universe cooled. The unified force cracked into the distinct interactions we now study in labs. The echoes of this rupture might still linger. Some theories propose that the asymmetry between matter and antimatter, the very reason we exist, was locked in during this phase transition, a cosmic defect in the breaking of perfect symmetry. Yet for all its elegance, grand unification remains tantalizingly out of reach. Magnetic monopoles, for instance particles with a single magnetic pole, predicted by many GUTs, have never been spotted, despite decades of searching. Their absence is actually one of inflation's early triumphs. The theory explains why we don't see them everywhere. Inflation's exponential expansion would have diluted these relics to near invisibility, leaving only a whisper of their existence. But that doesn't mean they're gone for good. Somewhere buried in cosmic rays or ancient rock formations, a monopole might still lurk, a smoking gun for unification waiting to be found. The real magic of these ideas lies in their audacity. They force us to grapple with scales and energies so far removed from everyday experience, they might as well be mythology. But that's the point, the first second wasn't ordinary. It was a regime where quantum uncertainty shaped the cosmos, where fields we've never detected dictated reality's rules, and where the tiniest fluctuations were stretched into the galaxies we see today. Every time physicists smash particles at the LHC or scour the cosmos for primordial signals, they're not just testing theories, They're peering through a keyhole into that first unimaginable second, searching for the handwriting of a universe still writing its own story. And if the inflaton or grand unification ever shift from hypothesis to fact, the payoff would be more than just another line in a textbook. It would mean we've glimpsed the gears turning behind the Big Bang itself, the machinery that transformed a quantum spark into a cosmos rich enough to wonder about its origins. That's the ultimate promise of the first second, not just to tell us how the universe began, but to reveal why it's the way it is, and what it might still become. Buried in the cosmic microwave background's nearly uniform glow lies an anomaly so bizarre, it's been dubbed the cold spot, a sprawling region of space just a bit cooler than its surroundings, stretching over 1 billion light-years across. At first glance it might seem like a minor statistical blip, but this isn't just random noise. The cold spot's temperature dips far beyond what standard inflation models predict, with odds of occurring naturally at less than 1 in 50. That's like rolling a die 100 times and never landing on a 6. Not impossible, but alarming enough to make scientists wonder if they're missing something monumental. One leading theory is as dramatic as it sounds. The cold spot could be a cosmic bruise, the aftermath of a collision between our universe and another bubble universe during inflation. Picture 2 soap bubbles grazing each other in a froth of multiversal foam, their brief contact leaving behind a chill in the CMB as space itself recoiled from the impact. It's a wild idea, but not unfounded. If eternal inflation is true, such collisions would be inevitable, and the cold spot's unusual geometry, its sharp edges and suppressed temperature, fit the profile of a gravitational shove from beyond our cosmic horizon. Yet skeptics argue there might be simpler explanations. The cold spot could be a supervoid, an enormous underdense region where the lack of galaxies and matter subtly cools passing CMB photons through a phenomenon called the integrated Sachs-Wolf effect. But here's the catch. Surveys like the Dark Energy Survey have mapped the area and found no void large enough to account for the temperature drop. Unless we're missing an unfathomably vast emptiness, one stretching farther than any known structure, the mystery only deepens. Then there's the nuclear option, exotic physics. Some theorists propose the cold spot might be a relic of a phase transition in the early universe, a moment when space itself underwent a sudden reorganization, leaving behind topological defects like cosmic textures or domain walls. These hypothetical structures would warp space-time in ways that subtly distort the CMB, creating localized cold patches. Others suggest it could be evidence of quantum entanglement writ large across the cosmos, a fleeting imprint from when the universe was smaller than an atom. The cold spot's enigma isn't just academic, it's a litmus test for cosmology's limits. If it's a multiverse collision, it would be our first tangible evidence of realities beyond our own. If it's new physics, it might reveal forces or fields that once shaped the universe but vanished without a trace. And if it's just a statistical fluke, that's almost more unsettling, because it would mean our most precise map of the cosmos still hides artifacts we can't explain. Future telescopes like CMBS-4 and the Simons Observatory aim to dissect the cold spot with unprecedented precision, searching for telltale patterns in its polarization or secondary imprints from ancient gravitational waves. Until then, this cosmic riddle remains open, a cold, quiet challenge to everything we think we know about the universe's birth. Whether it's a window into the multiverse or just a quirk of probability, one thing's certain: the cold spot refuses to be ignored. Hidden in the faint tremors of space-time might be the ultimate smoking gun for cosmic inflation, primordial gravitational waves, ripples left over from the universe's violent first moments. While we've detected gravitational waves from black hole mergers, these ancient waves would be something else entirely, a direct echo of inflation itself, stretching back to when the universe was less than a trillionth of a second old. Catching them won't be easy. Their signal is buried under eons of cosmic noise, but a new generation of detectors is gearing up for the hunt, and if they succeed, they'll rewrite our understanding of the Big Bang. Leading the charge is LISA, the Laser Interferometer Space Antenna, a daring mission set to launch in the 2030s. Unlike ground-based observatories like LIGO, which listen for high-frequency waves from colliding black holes, LISA will float in space as a trio of satellites separated by 2.5 million kilometers, forming a laser triangulated net sensitive enough to catch low-frequency ripples. These are the waves inflation would have imprinted on the cosmos, stretched to wavelengths so vast they'd make the Milky Way look like a speck. LISA design is revolutionary. It's essentially a galactic-scale tuning fork, capable of sensing distortions in space-time smaller than an atom across its entire array. But LISA is just the beginning. Concepts like the Big Bang Observer, or BBO, take ambition even further. This proposed fleet of space-based detectors would act like a microscope for gravitational waves, combing through frequencies with such precision, it could isolate inflation's signal from the cosmic background like picking out a single voice in a crowded stadium. BBO's secret weapon, its ability to measure not just the wave's presence, but their polarization, the specific way they twist space-time. Inflation's gravitational waves would have a unique polarization pattern, a fingerprint that alternative theories like bouncing cosmologies can't replicate. Finding it would be like stumbling upon the universe's birth certificate, signed in the language of gravity itself. The stakes couldn't be higher. If these detectors catch primordial waves, they'll do more than confirm inflation. They'll reveal its energy scale, telling us exactly how ferociously space expanded in that first instant. A strong signal might point to grand unification, the moment when all fundamental forces were one. A weaker one could hint at exotic fields or extra dimensions woven into the fabric of reality. And if they find nothing, that would be just as startling, forcing us to reconsider whether inflation happened at all, or if the cosmos began in a way we haven't even imagined yet. This isn't just about testing a theory, it's about opening a window into a regime of physics no particle collider can reach, where quantum mechanics and gravity collide. The gravitational waves from inflation wouldn't just be relics, they'd be messengers from a time before time, carrying secrets about how something as fragile as space-time emerged from the chaos. And with every advance in technology, we're inching closer to tuning into that cosmic broadcast, waiting for the moment when the universe finally tells us how it all began. The moment we try to peer into the universe's very first instant before even inflation began, we hit a wall where Einstein's relativity shatters. At these unimaginable scales, where space-time crumples into a froth of quantum uncertainty, gravity stops playing by classical rules. This is the realm of quantum gravity, and its clues might be hiding in the Big Bang's aftermath. Theories like loop quantum cosmology propose a radical rewrite of the cosmic origin story. Instead of a singularity where density becomes infinite, the universe could have bounced from a prior collapsing phase, like a rubber band snapping back after being stretched too far. Imagine the cosmos not as an explosion from nothing, but as a cosmic rebound. In this scenario, our Big Bang was preceded by a universe contracting under its own gravity, until quantum effects at the Planck scale, distances a trillion times smaller than an atom, generated a repulsive force strong enough to reverse the collapse. These theories eliminate the need for a singularity by introducing a fundamental granularity to space-time itself. Picture the fabric of reality not as smooth and continuous, but as woven from tiny, indivisible loops or pixels, a structure that prevents infinite densities by its very nature. What's electrifying is how these ideas leave testable footprints. If the universe bounced, the violent pre-Big Bang contraction would have amplified gravitational waves to deafening levels, potentially imprinting a unique swirl pattern on the CMB's polarization, one distinct from inflation's predictions. Some models even suggest a faint echo of the pre-bounce universe might linger in the distribution of galaxies, like a shadow cast across cosmic history. While current observations favor inflation, Anomalies like the CMB's large-scale power suppression keep alternative models in the game, yet the real promise of quantum gravity lies beyond competing origin stories. It could answer why our universe has 3 spatial dimensions, not 2 or 10, perhaps because higher dimensions compactified during the bounce, or because the loops of space-time naturally stabilize in this configuration. It might even explain dark energy as a residual quantum pressure from the bounce itself, a cosmic afterglow of that primordial rebound. The hunt for these clues is pushing technology to its limits. Future CMB experiments like CMB-S4 will scour the sky for polarization patterns that could betray a bounce, while tabletop experiments with supercooled atoms simulate Planck-scale physics in the lab. Whether loop quantum gravity, string theory, or some yet unknown framework wins out, one thing's certain: the Big Bang's first quantum flickers hold the keys to a theory of everything, if we can learn to read them. The universe's earliest moments weren't just the birth of space and time, they were the crucible where gravity itself was forged. Right now, the cosmic microwave background is our most direct link to the Big Bang, a glowing testament to the universe's violent birth. But what if we fast forward not billions, but trillions of years? The CMB won't just dim, it will vanish entirely, leaving any future civilizations in a cosmos with no memory of how it all began. Here's the brutal truth: the universe is stretching itself thin. As dark energy accelerates expansion, space pulls galaxies apart like bread dough rising in an oven, redshifting light to ever longer wavelengths. The CMB's already faint microwaves will stretch into radio waves, then infrared, then beyond detection as their photons lose energy to the void. By 1 trillion years from now, the afterglow will have redshifted so severely, its wavelengths will span light years, making it indistinguishable from the cold, empty background of space. The universe's birth certificate will have faded to nothing, but the CMB's disappearance is just the beginning. As galaxies beyond our local group recede faster than light, their light will cross a cosmic horizon, leaving no trace in the sky. The night will grow darker, star by star, until only the Milky Way and its merger remnants remain visible. Future astronomers born in this lonely epoch would peer into an abyss with no galaxies, no quasars, no CMB, just an endless void whispering no clues of a fiery beginning. Even the tools we take for granted would fail them. The Hubble constant, our measure of cosmic expansion, relies on spotting distant objects to track their retreat. In a galaxy-bound future, there'd be no reference points left to gauge expansion at all. Dark energy's dominance would be invisible, its effects playing out on scales too vast to observe. The universe's fate, a question without data, a mystery with no trail of breadcrumbs. This raises a chilling thought: we might live in the only era where cosmology is even possible. The 13.8 billion years since the Big Bang, just a fleeting window where the afterglow was bright enough to see, but the cosmos hadn't yet expanded into obscurity. Future scientists might never deduce an expanding universe, let alone a Big Bang, unless they uncover ancient relics, like our long-dead probes buried in the dust of time. Yet there's a poetic twist: even as the CMB vanishes, its legacy lives on in the very structure of reality. Those quantum fluctuations it preserved, they're the reason galaxies and thus civilizations exist at all. The universe may forget its birth, but the fingerprints of inflation are etched into everything, from the atoms in our bodies to the voids between stars. In the far future, the Big Bang story won't be written in light, it'll be written in us. From the cosmic microwave background's whisper of ancient light to the quantum ripples stretched into galaxies, these 25 discoveries aren't just milestones, they're chapters in an epic 14 billion-year story still being written. Each revelation peels back another layer of the universe's grand design, from the explosive burst of inflation that set everything in motion to the ghostly neutrinos that slip through our hands like cosmic shadows. We've traced the fingerprints of dark energy, decoded the universe's flat geometry, and even glimpsed the possibility of other universes lurking beyond our horizon. These aren't just abstract ideas, they're the foundation of reality itself, written in the language of gravitational waves, primordial magnetism, and the delicate imbalance between matter and antimatter. Every discovery is a puzzle piece, fitting together to show us how nothingness became everything, yet for all we've learned, the most humbling thought isn't just how vast the universe is, it's how fleeting our window to understand it might be. We live in a rare sliver of cosmic time where the afterglow of the Big Bang is still visible, where galaxies haven't yet vanished over the horizon, and where the tools of science let us reconstruct the universe's infancy with staggering precision. In trillions of years, the CMB will fade to nothing, the stars beyond our local group will disappear, and the evidence of an expanding cosmos might vanish entirely. We're the lucky ones, alive in an era where the universe still remembers its birth and shares its secrets with those willing to listen, so the next time you look up at the night sky, remember, you're not just staring at distant stars. You're seeing echoes of quantum fluctuations from the first trillionth of a second, relics of a time when the entire cosmos could fit on a pinhead. You're part of a story that began with a burst of inflation, sculpted by dark matter, and propelled by dark energy, a story with no known ending. And while we may never uncover every answer, the quest to understand our place in this vast inflationary universe is what makes us uniquely human. What cosmic mystery fascinates you the most? Is it the enigma of dark energy, the hunt for primordial gravitational waves, or the spine-tingling possibility of a multiverse? Let us know in the comments, and if you're hungry for more deep dives into space's greatest puzzles, hit subscribe so you don't miss the next chapter in our exploration of the universe's grandest mysteries. After all, the cosmos isn't just out there, it's unfolding all around us, and the adventure is just